Welcome to the Padhai Kar Lo JEE preparation channel. You can practice more problems on this exact topic on our Padhai Kar Lo Android app, link in the description below, or on our website padhaikarlo.com. Today's topic is electric current and Ohm's law, starting from the microscopic picture, or moving charges. Let's begin. Electric current is genuinely defined as the rate of flow of charge, I equals dq over dt, and at the microscopic level, current in a conductor arises from free electrons drifting slowly through the material under an applied electric field. This drift velocity, Vd, relates to current through I equals n times A times Vd, where n is the number of free electrons per unit volume, A is the cross-sectional area, and E is the electron's charge. It's genuinely worth appreciating just how slow this drift velocity actually is, typically only a fraction of a millimeter per second, even though the electrical signal itself travels through the wire at nearly the speed of light, since the signal is an electromagnetic field effect propagating through the entire conductor almost instantly, not the literal physical motion or any single electron. Ohm's law states that the current through a conductor is directly proportional to the potential difference across it, provided physical conditions like temperature remain genuinely constant, written as V equals I times R, where R is the resistance, a property depending on the material and the specific geometry, length and cross-sectional area, or that particular conductor. Resistance itself relates to a purely material property called resistivity, ρ, through R equals ρ times L over, where L is length and A is cross-sectional area. This separation is genuinely important. Resistivity depends only on the material and temperature, while resistance additionally depends on the object's specific shape. Materials that genuinely obey Ohm's law, giving a straight line V versus I graph through the origin, are called ohmic conductors, like most metals, at constant temperature, while materials that don't, like diodes and thermistors, are called non-ohmic. For most metallic conductors, resistivity genuinely increases with increasing temperature, since increased thermal vibration of the lattice ions increases collision frequency with the drifting electrons, reducing their effective drift velocity for the same applied field. For semiconductors, by genuine contrast, resistivity decreases with increasing temperature, since heating actually releases more charge carriers into the conduction band. This opposite temperature behavior is exactly why thermistors, made from semiconductor material, are so useful as sensitive temperature sensors. A frequently tested trap involves genuinely remembering that Ohm's law is not a fundamental law of nature the way Newton's laws are. It's genuinely an empirical relationship that happens to hold for many materials under many conditions, but fails completely for non-ohmic devices, and a question asking you to verify or disprove Ohm's law for a given VI dataset is testing exactly this distinction. Also remember that resistors in series always have larger equivalent resistance than any individual resistor, while resistors in parallel always have smaller equivalent resistance, exactly opposite to how capacitors combine. Let's recap. Electric current is the rate of flow of charge, I equals dq over dt, and at the microscopic level arises from a very slow electron drift velocity. Ohm's law V equals IR holds for ohmic conductors like most metals, where resistance relates to resistivity through R equals ρ L over A, remembering that metals and semiconductors have opposite temperature dependence, and that Ohm's law is an empirical rule rather than a universal law, are the keys to avoiding common errors. That's electric current and Ohm's law. Keep the ohmic versus non-ohmic distinction and the opposite temperature behavior, or metals and semiconductors, sharp. They're the foundation for the entire current electricity chapter. If this video helped, please like it and subscribe to Padhai Kar Lo for more JEE preparation content just like this. See you in the next one.